So we just have one more session, and here I want to cover geographically weighted regression and then random coefficient variation, which are two more ways to deal with spatial heterogeneity. And when we saw the expansion method and also the multi-level approach, the essence was to build in the variability of the parameter through some auxiliary regression, either at the same level as was the case in the expansion method, or at a different level as was the case in the multi-level approaches. The geographically weighted regression approach lets the data drive the variability in the parameter. And before we get into the specifics of the method, I want to spend just a few minutes giving some very quick background on a non-parametric approach and where this comes from and how this can then be incorporated into modeling the variability. The geographically weighted regression is a special case of what is referred to as local regression. And you can think of this as an unspecified functional form. So we have observations on y at I, and rather than specifying, as we have so far, xi beta, which is a linear regression, we have an unspecified m function of x of I. And to set the stage, think of a situation which is typical in many experiments, where you just have a finite number of values for x. Let's say a dosage type of situation. So you give medicine, you give it for 2 days or 5 days or 10 days. So you have, a finite number of points on the x-axis, and then for each of these people, the people in the experiment, you have various outcomes. Some response, temperature, or whatever, blood content measure. So you can think of the scatter plot as consisting of a small number of finite locations on the x-axis and then a bunch of points vertically for each of these x points. So then we can compute, without imposing any functional form, the mean, the conditional expectation of y given x as simply the average of the y's for each given x. Now this is not a smooth function, it's just a number of discrete points, but it doesn't impose linearity or any functional form. The data tell us these are the estimates of the conditional mean of y given x, given a discrete number of values of x. Then we can extend this and think of a situation where there's actually multiple values of x, a continuous distribution, so the number of y's that match any individual x will no longer be multiples. So, or there may be one or two, but it's going to be much smaller than when we have just a finite number of x values. So then computing an average for those y's doesn't really work anymore. But what we can do is, say, group x's that are close to each other and then compute the average of the y's in that bin, so to speak. And we can go even further and make this a moving bin. So at each point on the x-axis, we can think of a bin that contains some of these y variables, and we compute the average of these y variables. That is a notion of a local mean, or a local weighted average estimator. So we just start conceptually with a single x and multiple y's for that x, to multiple x's, and then maybe 1 or 2 y's for those, but we still compute the mean non-parametrically by just grouping the x's in a bin. Then we can go even further, and rather than saying we just group them in a bin and treat them all as if they have the same contribution, now we put in a weighting scheme. And we treat, still we're moving across the x-axis, and say at any given point, we take the x's that are close to it, but we weight them differentially. And we weight them in such a way that the further away they are, the less weight they get. So now we have a moving average, a moving weighted average. For every x point, we can compute the conditional expectation of y as a weighted average of the y's that we see in that bin, where they are weighted depending on how close the x's are to our focus, to our x in question. So the x naught in this notation is the one in question, and then the other x's are surrounding that. So we can think of this as some kind of a bandwidth surrounding our focal point, and then estimating the average in that bin. And that is our measure, non-parametric, there's no function here, of the conditional mean of y given x. So given x, what can we expect y to be on average? And then we can extend that even more and come up with specific types of weights to carry out this weighted average. And one particular type of weight that is used very often is a kernel weight. And a kernel is nothing but some function that weights observations differentially depending on their distance from a focal point. So the focal point is still x naught. The xi are the different observations. Their weight is determined by this kernel function k. And a kernel function is a function that it's like a probability distribution. It's very similar. It gives lesser weight as you move further away from the focal point, and it adds up to 1. It's symmetric, so both sides of the focal point get equal weight. And you just stick basically the difference between the focal point x naught and xi into that function, and out comes a weight. And then the outcome is still a weighted average, but we call it a regression because we include explicitly both the x's and the y's. But in essence, it's still a weighted average where the weights follow this kernel function. Now, there are two important aspects to the kernel function. One is the function itself, and we'll see some examples in a second. The other one is the bandwidth. And the bandwidth is, if you wish, the bin, is where do we cut it off. Remember where we came from. We started with individual x's, and then we put in a bin and took the average of all the y's in the bin. How wide is the bin? That's the bandwidth. And so obviously, if your bin is very wide, you're in essence taking the average of all the y's. If the bin is very narrow, you're going to take an average of very few y's. So maybe the bias will go down, but the variability will go up because you have fewer points to take an average from. And this bias variance trade-off is the essence of the choices one has to make in these type of non-parametric approaches. So you can choose a different kernel function. In the end, it doesn't make that much of a difference. What does make a big difference is the bandwidth. In other words, how many of these x's do you bring in to compute this varying slope as you move through the data space? And this is a bivariate example. You can extend this to multivariate situations as well. And the key is that the kernel, if you think of 2 dimensions, you have a certain density. Now add a third dimension, then the boxes of your 3-dimensional classification can become sparse very quickly, in that you don't necessarily have observation points that match a range on 2 or 3 variables. Income between 10,000 and 15,000, house price between 100 and 120,000, rainfall between this and that. And if you have too many combinations, you can think of these as boxes. There's nothing in the boxes. And that's a problem with multivariate kernel estimation. If there's nothing in there, there's nothing to compute the averages from. So in a multivariate context, it becomes very tricky to get the right kernel function so that you grab enough data points, but not too many, to have the variability in the estimate. In 2 dimensions, it's pretty straightforward. So this is then this notion of a kernel regression. Some examples of kernel functions are Epinechnikov and Bi-square. There's a whole bunch of them. I won't In fact, if you go to the spatial weights chapter that I mentioned the other day, there is a discussion of kernel weights in there as well that gives you the specific examples. There's a major qualitative difference between some of these kernel functions. These bi-square and a triangular or a uniform, they all have clear cutoffs. In other words, data points outside the bandwidth do not contribute to the estimate. In contrast, a continuous function like a normal Gaussian kernel, it goes to infinity. So in principle, every data point contributes all the time. But of course, because of the decay, more remote data points will not contribute very much. So for all practical purposes, there is a practical bandwidth, which means that once you're beyond this point, your contribution, the contribution of these observation points becomes very, very small. But in principle, a continuous kernel like a Gaussian kernel brings in all the data points. So there's no absolute cutoff for a normal kernel, which is simply a Gaussian function. You know, you stick it in the exponential, and you, because of the way the bell curve works, you know, when it starts to go down, meaning the weights become very, very small, is related to the standard deviation or to the variance of the distribution. So indirectly, you can come up with an effective bandwidth by specifying the variance for your Gaussian kernel. The larger the variance, the flatter the function, so the more weight, more remote points get. The smaller the variance, the spikier, the steeper the function, so the less weight, more remote points get. And the choice of the bandwidth is very difficult. And so there are a number of techniques to come up with an quote-unquote optimal bandwidth in the sense of an optimal trade-off between bias and variance. You know, you can always overfit, which gets you a perfect fit, or you can underfit, which gives you too much variability. There's a trade-off involved that has to do with the particular objective function that you specify of how you combine the bias and the variance, and then you can come up with some rules, or you can do cross-validation, which is a more of data-intensive measure that finds the best combination of these, the best combination in terms of the bias and the variance by experimenting with different bandwidths and using some criterion, an information criterion or some fit criterion to stop and pick the best one. We'll see in a second that it does matter. So given this background, this is just a little quick background on a non-parametric approach to regression modeling. So we don't impose any functional form. It's essentially a combination of weighted averages where the weights are determined by this kernel function. In geographically weighted regression, we approach the same problem as before, the extreme heterogeneity. So every observation has its own beta I. And how do we model the variability in the beta I, extreme heterogeneity? Rather than modeling that variability through some other variables, auxiliary variables, as in an expansion method, or at multiple levels, as in the multi-level modeling, we let the data determine the variability. In very much the spirit of non-parametric regression, in that we'll let the parameter that is the slope coefficient that is estimated be a function of the local observations. And local, in this sense, not in a parameter space, as it is originally in non-parametric, but in geographic space. So that the data points that are used to get the estimate of the slope, let's put it that way, are the data points that are close to the given observation. Not close in terms of the xi on the parameter and in the variable space, but close in terms of latitude and longitude in geographic space. And that is the difference between, say, a standard local regression in standard non-parametrics and a geographically weighted local regression. The domain over which the neighbors are determined is a geographic domain rather than an attribute domain, a variable space domain. But the principle is the same. We're going to get our coefficients by a locally weighted average. Local now meaning within a given distance geographically from our reference point. And we'll apply a kernel function to do the differential weighting that determines the contribution of each of the observations within the bandwidth to the estimate of the slope or the coefficient. So the way this is implemented is by using a kernel function. So the closer observations get more weight. The practical implementation requires a choice of a specific function, say a bi-square or a Gaussian function, but also the choice of a bandwidth. And the intuition is very simple. The larger the bandwidth, the smoother their estimate. The tighter the bandwidth, the spikier the estimate. So if you think of a regression geographically, if your bandwidth is so large that it includes all the points, then you end up with a constant slope. If your bandwidth is so tight that it only includes the observation itself, then the system breaks down because you have one observation, one data point for each location. So then we're back in where we started with the extreme heterogeneity as an incidental parameter problem. So the GWR is some kind of compromise between the two that determines an optimal bandwidth so that there are sufficient data points within the kernel to get a reliable, in terms of variance, in terms of standard error, estimate for the slope with those data points, but not too big a bandwidth so that there are too many data points so that the heterogeneity is washed away. No. If you take all the data points in, then there might be heterogeneity, but you don't get it because you include everything, so you're back with your constant slope. Whereas if you take too few data points, you get the heterogeneity, but because the precision of your estimate is a function of how many data points you use, if you only use 4 or 5 data points, there will be a huge standard error around these estimates. And so then the interpretation becomes very difficult, because even though you may map the point estimates, and this is what we end up doing, the variability around these point estimates may be so great that it may give you a spurious impression of heterogeneity, or it may actually be homogeneous, but it looks like it's heterogeneous. So this is an issue one encounters when using GWR. It's always this trade-off between bias and precision. And the choice of the bandwidth is the problem of the choice of the bandwidth is how we obtain a solution that is a compromise between these two. Now, one way to approach this is to find an optimal bandwidth, one size fits all, so the bandwidth is the same everywhere in geographic space, but also in variable space. This is a problem whenever we have very sparse distributions. So if you think of the data as data points in space, if you have cluster points, there's no problem. You just put your kernels over it, you will always have sufficient data points. But if they're very spread out, then if you have a fixed bandwidth, and that bandwidth is not large enough to pull in sufficient data points, again, you will have the problem of too great a variability of the estimate. So one way to deal with this is to have an adaptive kernel, where the adaptive part is not with respect to the kernel function, but it is with respect to the bandwidth of the kernel. So you ensure that for every estimate that you make, there are at least n data points, whatever n may be. That's a function of the data. So let's say you ensure that you have at least 20 data points for every parameter estimate. So that means that in the denser parts of your sample, the bandwidth will be smaller because it doesn't take that much to get 20 other data points. But in the sparser set of your data set, the bandwidth will increase up to the point that it catches 20 observation points. And so that's the notion of an adaptive bandwidth. So this is a picture out of the GWR book where you see on the right-hand side the two different cones. One is narrower in the part of the data distribution that is more clustered. The other one is wider in the part of the data distribution that is more sparse. So that's the notion of an adaptive kernel. So what actually happens then in the GWR, we essentially run a separate regression for each reference point. We put our cone, our kernel around that, grab our observations, and get a slope. And then we move it and do it again. Now, in a nutshell, it's actually can be expressed using a weight, where the weights are not the kind of weights that we get, that we've been using so far, but these are weights that pull in the proper locations. So say for observation number 1, our weights will pull in the 20 neighbors for that observation. They don't have to be observation 2, 3 to 20, but they could be, 48, 96, 55, depending on how the data are arranged in the data matrix. So that's what this weights function does. It picks out the correct observation points to be used in the kernel density, and then in addition to picking them out, which is a bandwidth issue, it also gives them the proper weight. So the proper weight is obtained by taking their distance to the reference point, sticking that distance in the kernel function, and that yields you the weight that that particular observation will contribute to the estimation of the slope at that point. So in essence, you can summarize it all in this one expression here, but you can also think of it as some kind of cone moving through the data set and recomputing a weighted estimate of a slope at each reference point. And that then, because it is specific to location, because it is specific to x and y coordinates, you can map the spatial distribution of the coefficient. And here it is that things get a little tricky, because in what I would call a naive application of GWR, the precision is often ignored, and you just map the point estimates, which, as I mentioned a minute ago, can be highly misleading if the variability, if the precision of the estimates, especially when you use a fixed bandwidth and the distribution of your data points is not homogeneous, is not nicely uniform throughout the data set, you will have very different precisions between the dense parts and the sparse parts. And that should be reflected in your visualization in one way or the other. So to illustrate this, I ran this on the Columbus data one more time, and I was particularly interested in the variability of the housing coefficients. And so what you see in this graph are 4 box maps. The one on the left is the one that we obtained from the expansion method. So in the expansion method, we simply use the linear trend surface in the x and y coordinates. So we can, for each, this is Columbus, 49 observations, for each of the 49 neighborhoods, we know the x and y, we plug it into the expansion equation, and we have a different beta. And then we look at the spread of the beta, and that is the box plot on the left. So you see it's relatively symmetric around the mean. The mean value will then be related to the overall fixed regression coefficient. And then the next 3 graphs are the distribution of the parameters using a GWR approach with different bandwidths. The first one is with a ridiculously large bandwidth. And what you see is that the distribution is very compressed. It's very close to the median value, because in effect you are using almost all the observation points, almost the same observation points for each location. That's what happens when you have a very, very large bandwidth. Then the middle one is the optimal bandwidth that GWR picks using a cross-validation criterion. And here you see something very interesting, is that, the spread is very similar to what we had in the expansion method. but we have some outliers. We have some extreme points both at the high end and at the low end in that distribution that is obtained by the kernel, the moving kernel estimation, if you wish. And then the one on the right is one with a ridiculously small bandwidth, where the distribution is extremely spiky, and you see a much wider range around the median, and you also see 5 outliers in this case. And you know, Columbus is only 49 observations, so 5 outliers is 10% of the data points that are outliers, which is quite a bit. So this gives you a sense of what you get when you play with these bandwidths in terms of the variability of the individual coefficients. So this is a non-spatial distribution of the location-specific coefficients, and then the spatial distribution you get by mapping them. And the first map is the one that we get when we use the optimal bandwidth. And I think it's really interesting to see how similar this is to what we obtained for the spatial expansion method. The spatial expansion method imposed a linear trend for the variability of the parameter. The GWR extracts a linear trend, or something very close to a linear trend, for the variability of the parameter from using the data. And so that's the main difference between the two. One imposes a functional form and imposes the covariates that drive the variability. The other one extracts the variability from the data by moving this kernel around. Now, I also wanted to illustrate what happens when your bandwidth is, as I said, ridiculously small. So when I tighten the bandwidth and use 2, these are arbitrary units. There's no particular meaning. Just 2 is 1/10 of 20. That's how you can think of it. And then you see it becomes much spikier. There is much more variability. There's some suggestion of a peak somehow in the middle rather than this nice linear movement from the northwest to the southeast. We see that there is kind of a hill in a spike in this area here, and then again a spike towards the tail end. But the larger bandwidth misses that additional variability. And the question then is, to what extent is this impression of difference correct in a statistical sense? And for that, you need to bring in the standard errors to see whether these are actually significantly different. But this is something, this is usually where I stop in my use of GWR. There is a growing body of applications of GWR that extends this to other types of models, to nonlinear models, to logit and count models, and has different specification tests associated with it. I like it as an exploratory technique. The reason why I don't want to push it further is because in the end we haven't really explained anything. What we find is clear evidence that the relationship that we posited, our regression relationship, is not stable across space. What we haven't done is explained why it is not stable across space. So it is a powerful technique in that it gets around this problem of us a priori imposing how the parameter will vary. But it shows us the parameter variability from the data, and then we can go back and say, well, this is correlated with these other variables that we then could bring into the model. And once we have a model for the change, which is really what the expansion method and the multi-level methods are trying to do, is models for the change, then we can think of that more as explaining in the sense that we could see what happens if we change some of these z variables, for example. You can't do that in GWR because GWR is driven by the data. We can't, experiment with the variability itself. But I think it's a very useful technique. If you have any doubts at all about the stability of your coefficient, and it makes for great maps. You know, if you want to get a point across, this will do it. The problem in the implementation of GWR is the same problem as in any kernel process, kernel estimation. It's the bandwidth. What is the optimal bandwidth? And what you do find is that the results are quite sensitive to the bandwidth.
How did you decide that the middle one there was the optimal bandwidth? Was it based on residual mean square error criteria, or just to look like closest to the expansion method?
No. It's I actually used, and in fact you'll go through this in the lab, or you can. They're the same examples. I used the cross-validation criterion that there are a number. I mean, if you go to the GWR book, there are a number of different criteria one can use. One is an information criterion. One is a cross-validation. It's kind of a fit measure. So I just ran that in R, and 20 is what it came up with as the optimal one. And then I thought it was very interesting that the spread around the median was very similar to what we had in the expansion method, and the map was very similar. But that's just a coincidence. It makes for a nice illustration, but there's by no means any guarantee that that will always be the case.